Okay, so our final speaker is Adam Chlipala. He's an associate professor in E&CS at MIT. He's made significant contributions in the areas of programming languages and formal methods, and he's written a well-known book titled Certified Programming with Dependent Types. And more recently, he's broadened his work to include other aspects of computer system design and implementation. So we're super excited to have Adam here to bring more of a programming language perspective from a lot of what we've heard today. More specifically to discuss some recent work he's been doing on formal methods and provable open source hardware design.
All right, thank you. So as the introduction indicated, most of my background is more on the software side. And about 5 years ago, I got pulled by a student into computer architecture and the use of formal methods there. So I want to try to tell a story of how we can take approaches that have typically only been found in the software world and then realize some of those benefits for architecture, and it'll maybe, I hope, fit these keywords of agility and openness. So the story that we're used to in building hardware is that we do verification, but I've learned this word just means run lots of tests most of the time. But sometimes we do formal verification, which means we're able to prove invariance for some executions. And what I'm more used to doing is what I would call full formal verification, where we actually prove complete adherence to the spec of an instruction set, to the level where we can actually know that, say, you run some function in machine code and it gives you the correct answer running on your processor. And we can even go further and think about the rest of the computing stack with the software layers as well, using multiple programming languages that have compilers gradually lowering them towards what the processor speaks natively. And I'd like to suggest that we try to do what we call end-to-end verification and show that all the layers of your system working together are able to provide the abstraction of correctly computing some function or whatever else. And this is a lot easier to do when we have open designs where we're able to reason about the implementations of all the layers of a complete computing stack. So to tell you a bit more about the approach that my team has been following there, let me introduce some of the tools and the terminology. We're doing what are called mechanized proofs, which basically means we're doing formal mathematical proofs that are checked by algorithms. And we do that using a particular theorem prover called COQ, C-O-Q, which is developed at INRIA in France. And to use this system, you encode some description of the artifact that you're looking to verify. It could be code in a hardware description language or a software programming language, explain mathematically what that is, feed it into this general purpose theorem prover, and also write down some sort of mathematical specification that constrains what behavior you're expecting from this system. And most labor intensively, write out a mathematical proof establishing why this system meets that specification. And probably some of you at least have seen mathematical foundations like ZF set theory, which have notions of what are the acceptable inference rules you can use to draw conclusions in math. Think of an ASCII language for writing out that kind of proof, which can then be checked by an algorithm. And the proof checker is completely independent of the application domain, doesn't know anything about hardware or software. We're encoding all of those in a more general mathematical language. And what I'm also suggesting we do is what are called proofs of functional correctness or full functional correctness, where we go beyond generic properties. And in the software world, the classic example of that is this program doesn't crash or it doesn't have a seg fault or that kind of property. Instead, we should prove functional correctness with specifications that are quite specific to the particular artifact that we're analyzing. Say that a particular program always outputs the right answer, where we very carefully define what makes an answer correct. And in the setting of hardware, this might be, instead of just proving a selection of invariants for your cache coherence protocol, you actually define what it means for a cache coherence protocol to provide the illusion of sequential consistency. And you actually prove that your protocol in its realization in RTL truly acts like a sequentially consistent memory. Finally, I'm arguing for what we'll call end-to-end proofs, where we have a system divided into a series of layers, some of them hardware, some of them software, and each one of them has its own formal specification and its own machine-checked proof of correctness. And we go through the exercise of connecting all of those together to get a guarantee about the whole system considered as one unit that is supposed to provide some application of interest to real users. So getting into our particular case study here, we've basically been working towards building a verified Internet of Things light bulb. It's cutting-edge technology, including this Sci-Fi development board in the middle there. Basically, our approach has been to start out with open source designs and freely available hardware around RISC-V, and then successively replace pieces of that with new designs that we have formally verified in the way that I'm selling here. So we have our own alternative processor that's been defined in an HDL that I'll get to, that has a formal mathematical proof of correctness, and we're planning to swap out that middle board for an FPGA running that hardware design. Down below here, you see the Ethernet connection by which this system takes in commands asking to turn the light bulb on or turn it off. And off to the right, we have a power strip with a convenient GPIO interface that we can connect to this processor. So we're really just turning the power strip on and off, and the light bulb gets plugged into this. But the whole thing really works in a student office, the most convenient way yet to control the lighting of your workspace. So we're trying to prove basically all the digital parts of this system correct in a unified way. So that means we have the hardware pieces, the software pieces at some level. From a user's perspective, these are all lumped together into some system with a set of I/O pins that connect it to the rest of the world. And some of these pins we think of as input and some we think of as output. We want to write a formal specification about how these pins are supposed to be set at different times that captures our idea of a correct controller for this light bulb. So the way we do that is thinking in terms of all the traces that this system could generate. We're going to measure the pins at every clock cycle, and any execution of the system generates a trace of pin values over time, and we're going to constrain which such traces are acceptable, which represent correct execution of the system. So for the input pins, these are really up to the environment to set. The network sets these for us. We don't get to constrain what values might be on the input pins, but the output pins are a different story. This is really our job as specification writers to decide what are correct values on the output pins at every instant in time. So for this particular example of the light bulb controller, basically we're saying that there's a particular output pin that controls whether the light bulb is on or not, and its value should depend on whether the last valid Ethernet packet that was streamed in over the input pins said turn on light bulb or turn off light bulb. So you can formalize this in logic and math, exactly what this means as a predicate over these traces of instant readings of the values on these pins. And we build up to this whole system specification by proving properties of the individual layers of the system. And at the center of it all is the formal semantics of one of the variants of the RISC-V instruction set. We've been developing the semantics as part of the ongoing effort within the RISC-V Foundation, which has led to a number of candidate formal semantics. On top of that, we can prove that a particular verified piece of hardware is exporting that semantics, but realizing it by a design in RTL. We can get to the software programming language on top of the instruction set. Our language is called Bedrock. You can think of that as a simpler replacement for the C programming language, which is more pleasant to use in formal methods without taking on the full complexity of C. So we've built a compiler from that language to RISC-V machine code, which itself has a proof of correctness. And then on top of that, we have the particular controller software for this application, along with the application-specific specification, which again is a predicate on traces of I/O interactions. So all these pieces compose together, and we get the system that can meet the specification I just talked about. So let me start by saying something about the ISA spec in the middle. A common question that arises talking to hardware engineers is, what really is a specification? It seems like kind of a suspicious idea that when you see a spec, it just looks like another implementation of an API. And at some level, that's what a spec is, but it's a particularly tasteful implementation of an API. So what does that mean more concretely? It's written to convey behavior and not to run fast itself. We don't want optimizations to complicate the spec, because that makes it harder to understand what kind of rules it's trying to impose. So for instance, this is a reason why the canonical RISC-V simulator Spike, written in C or C++, is not appropriate as a formal specification, because C and C++ are quite unpleasant languages to reason about, especially when you try to get completely formal about it. But even just for humans trying to understand what's going on, not the most direct way to write things out. We also want a spec to be completely flexible in that the informal specification of an interface provides some dimensions of freedom to designers. You might have some implementation-dependent behavior, for instance. We often see that in a document. And a good formal spec should allow the full range of implementation choices that the informal spec is trying to allow. And then coming back to Spike here, there are some effectively hard coding of choices along some of these dimensions, which make Spike not fully general and therefore not suitable as an official formal spec. So the spec we've been developing is a functional program written in the Haskell programming language in a carefully chosen subset of Haskell that we hope will be readable to the full range of stakeholders who care about the meanings of RISC-V machine code programs. I've shown two example snippets here of the semantics of two RISC-V instructions. At the bottom is a more complicated one, sret, which has to do with returning from a system call, or that's how I think about it. And up top is a more elementary one, LW for load word. The important thing about this spec is it includes some operations whose meanings we're not really mandating. I've bolded and underlined those operations here. The examples in this case are get and set operations on registers and memory. And the idea is different RISC-V platforms will actually have different meanings of these basic operations, and we want to be able to define instruction meanings independently of those platform details. So let me say a bit more about how that works. One simple instantiation of this spec, where we fill in definitions of those bold underlined operations, is a straightforward single core semantics, where we just consider that registers in memory are simple arrays, and get and set operations access them directly. But we could also support multi-core systems with weak memory semantics by keeping the simple view of registers, but saying that now get and set operations on memory are touching some pretty complex axiomatic model where you have to go run an alloy model or something to figure out what you should return next. But we get to reuse all the simple instruction definitions from before. We just give alternative definitions for the primitives that the instructions depend on. And relevant to the particular case study I'm talking about here, we can define an alternative version of these operations that supports memory mapped I/O with an idea of which memory addresses are actually standing for ports communicating with different devices. And so when we touch a regular address, it gets the normal array kind of handling. When we touch one of the special addresses, if it's a write operation, we just add it to a log, which is a new part of the state associated with the core. And when we perform a read operation on one of these special addresses, we actually non-deterministically choose what value is found in that address, and we add to the log a record of which non-deterministic choice we made. But again, the basic instruction definitions are independent of these kinds of complications, and yet we can use them to describe MMIO as the unifying way that our processor can talk to the rest of the world. So now let me get to the way we define our hardware that we're going to formally verify to meet that specification. We're using a variant of the Bluespec high-level hardware description language. And basically the idea of Bluespec is that it brings something of a software-like object-oriented perspective to hardware design. And we break our hardware designs into modules, which are sort of like objects in Java. Each of them has its own mutable private state fields, which we would call registers in the hardware setting. And we access that private state not directly, but only by calling public methods on these modules. So think of this as, say, we're building a FIFO, and there are NQ and DQ methods. And each of these methods itself can call methods of other modules, just as like we'd expect in a software program. A key part of the semantics of Bluespec is that method calls appear to execute atomically. You can think of that as a method call takes one clock cycle. And therefore, we can semantically, if we want to get to the correctness of a design, we can think about, in a single clock cycle, which interactions can happen with other modules in the system. So we can have incoming calls to the methods provided by this module, and then in turn, this module might make calls to methods of other modules. Let's just log all of those calls, the names of the methods that are being called, along with the argument and return values that show up. So any module has associated with it a set of all possible single-cycle interactions that it might participate in. And the key way we do formal verification is we relate complex optimized modules to simpler reference implementations. And we compare the set of all interactions that the optimized module might have with the set of all interactions that the spec might have, and make sure there's an appropriate subset inclusion relationship between those. And this turns out to be a nice modular way to think about dividing a design into pieces, proving each one separately, and then composing the results together into, say, a result for your full processor or your full processor plus cache memory system. So the way this works, as we gradually link new modules into our implementation, we stop recording in these traces all the calls to the methods of the module that we've linked in, because those calls become internal implementation details, not relevant to the functional correctness of this implementation. And I'm going to link another module on the right, and you'll see one of the calls in the thought bubble on the right disappears because now it's to a method that is considered internal to the new larger module we've built out of smaller ones. So this is the key to giving us design flexibility while still having relatively simple specifications that are pleasant to prove other properties against. So what this means is that we can take some sort of SOC where we have different pieces, like, say, on the left I have the real implementation, an optimized processor, a cache memory system, some carefully optimized software code. We want to prove this equivalent in some sense to a reference implementation with a much simpler processor, a naive memory, and some straightforward software. The proof tools that we use make it possible to decompose this into separately reasoning about the pairwise equivalence of the three main parts of this system. And this is all justified in a mechanized proof system and proved sound basically from first principles, starting on top of set theory. You can show that this sort of decomposition works, and then practically speaking, we actually can do the proofs about these three parts separately. So let me now turn to the software piece of this. This is an example of a routine that appears in our implementation of the light bulb controller. It deals with receiving one packet over Ethernet. And for this audience, I probably don't have to say too much about what it means to have an embedded domain-specific language for hardware design. And that's roughly what we're doing here for software. We've embedded a C-like programming language inside the functional language of our proof tool, much as Chisel is embedded inside Scala. And that's why the concrete syntax is a little wonky in some cases. But this is very close to looking like familiar C code. And then to verify that this is a correct implementation of the light bulb controller, we have to write a formal precondition that says what we assume about the machine state at the point where we jump into the beginning of this code. This includes not only the register and memory values, but also a log of all MMIO interactions that have happened up to this point. And then we also write a formal postcondition, which is what we must now commit to guaranteeing about the machine state when we reach the end of this code. So the memory and registers are in the right state, and we've advanced the log of MMIO interactions into the appropriate place, which basically captures the idea that we've read one Ethernet packet off of the appropriate input wire. We also have to provide a loop invariant associated with the one while loop that appears here, which captures what we know is true at the beginning of every iteration of this loop. And given these ingredients, there's a recipe for reading off some logical proof obligations that need to be established, and we prove those with a mix of human effort writing out proof steps and calling out to automation that fills in some of the more tedious details between those human meaningful steps. So this is how we can prove the correctness of the particular controller software at the top of all this. Then we need to compile that software into RISC-V machine code. The software we wrote, using the formal semantics we've written of the Bedrock software language, which is at some level similar to the semantics of the RISC-V machine code language, tells us what is the set of all possible I/O traces that this software might produce. We can then apply our compiler to generate machine code. Then we have the instruction set semantics, which tells us what is the set of possible I/O traces for the machine code. And we also prove a correctness theorem for the compiler, which effectively guarantees an appropriate subset inclusion relationship between all the I/O interactions that might happen at the compiled level versus the source level. And we're actually going to take this kind of subset inclusion and push it all the way up our stack of components. So recall this diagram. We're going to prove a subset inclusion between everything the RTL could do and everything the ISA says is supposed to be able to happen, and then another inclusion from what the ISA says can happen to what the programming language says can happen, and then from there, from programming language to the trace predicate we've written directly, saying what are the top-level I/O interactions that our controller is supposed to be able to have. Once we've done all these proofs, we can draw a box around most of the interior of all this and consider this is our digital system. It is using RTL to implement a top-level trace predicate. And we have to be very careful that we get right the definitions of what the top and bottom layers of this picture mean. But a cool thing that happens with this style of formal methods is that everything I've hidden with this box that I put up is no longer trusted. If we made any mistakes, for instance, in the formal definition of the RISC-V instruction set, we'll catch those mistakes in the course of doing this overall system proof. So that semantics is no longer trusted. It's no longer an opportunity to introduce bugs in the system. So this kind of approach really changes the story for how we can have rapid iteration through experimenting with new kinds of hardware and software architectures. We can go from the traditional setting in hardware development where you have some IP block, and every time you evolve the definition of that block, you have your pretty big verification team that's worried about generating enough test cases to catch any mistakes that might have been in that IP block. Every time you change something, there's a significant verification effort, if for no other reason than to rerun lots of simulation test cases. With this proof-based approach, you can instead, if you wrote your proof correctly with the right kinds of automation, when you make some changes to your IP block, you can rerun your proof completely automatically without new engineering effort. And if the proof checker gives you the thumbs up, then you're good. Otherwise, you might have to put in a relatively small engineering effort to update the proof. And you might have to worry about whether you have the right formal specification that the proof is establishing if you're at one of those top and bottom layers in the picture I just showed you. If you're at some interior layer, then the very process of doing the proof is guaranteeing that you'll shake out any specification mistakes there. So this can dramatically lower the human effort associated with evolving some piece of your system over time, whether it's a hardware piece or a software piece. What you can imagine building with this kind of approach is a marketplace or an ecosystem, whether it's commercial or open source, where there's a whole library of pieces out there that you can assemble into systems. Processors, compilers, software libraries, accelerators. Each of these, imagine, is out there on GitHub maybe with a formal specification saying what this piece is supposed to do, and also a proof, which establishes that this piece really does what it's supposed to do. So what that means is when you're building some sort of new system, you can pick and choose from this library of components, assemble your favorite ones together into one system, and then in a relatively low-effort way, compose those proofs together into the new proof that your full system meets the natural application level specification for it. And you don't need to trust any of the verification teams behind the components that you assembled together, because they produce these proofs which can be checked algorithmically against specifications which you can audit independently without even necessarily needing to read the implementations of all the pieces that you've composed together. So this is the real promise of open components in this kind of setting, both hardware and software. If we commit to distributing these artifacts with their machine checkable proofs of correctness, then we should be able to dramatically short-circuit the verification process for putting together new systems and reaching the highest levels of assurance in their correct operation. And I think I'll stop there. Thank you.
So Adam, it sounds like magic. It sounds too good to be true. Surely there must be some downside.
Burning out your graduate students is the main downside.
Burning your
Writing proofs all day, yeah.
Can you talk a little about the scalability? Like how will this scale up to more complicated, something beyond the IoT light bulb?
Yeah, there are all sorts of open research questions there. There's this whole discipline of mechanized proof engineering that's still at a relatively early stage. And it's hard to predict exactly which challenges come up there. But a lot of them have to do with performance of the proof finding process, because asking people to find all the proof steps themselves is pretty intractable. So we use a lot of automation, and at the same time we want to output arguments from first principles every time the automation works, which creates some interesting scalability challenges that we're still working out.
So one challenge of formal verification is like unpredictable interrupts. So how,
Interrupts.
Yeah, how do you?
You mean you're verifying an artifact that has to be prepared to respond to interrupts. That's the challenge?
For example, like some device, some sensors, they may generate interrupts to the CPU, but it's unpredictable. How do you deal with this situation? It seems like open system, like secure L4, SE L4, they are able to do formal verification
You mean they disable interrupts at certain points and make the task easier than would be realistic? Is that what you're saying?
I think maybe interrupts will be making things.
It's definitely a source of challenge, like any kind of concurrency is in formal verification. But there's been a fair amount of work in formal reasoning about interrupts, say, in the PLDI community. And there are modular techniques for, say, verifying your processor independently of knowledge of which interrupts are going to come in when. It's kind of hard for me to explain details on the spot here. I'm not sure I'm even up on all the latest details, but we're using such an expressive mathematical framework that if there is any kind of convincing argument for why an artifact is correct in its handling of interrupts, we should be able to encode it here. And the question is just what's the labor cost of getting that proof written? And since I'm not sure anyone's done that kind of proof yet, we can only speculate at this point, but it should be doable. Should I pick? No. Okay.
I wonder, in terms of skills, based on the experience, are they transferable to some guys who are good at writing code would be good at writing proof? Or it's sort of different kind of mindset so the person not?
There are some new skills to learn to get started in proof engineering, but I think people who are really excellent software developers have a decent chance of finding that they can develop those skills relatively quickly. And there's a lot of overlap because we're effectively doing programming to find the proofs for us. So it really is software engineering at some level. And say anyone who has a lot of experience writing compilers especially has a good chance of being good at writing proof finding functions.
One last question, Jared. What about hardware engineers?
Yeah, that's a tougher one. And there are these separate questions of what people are theoretically capable of learning to do versus, because of the social context, what they feel is part of their job description. I know there's a lot of resistance from hardware engineers to writing in languages other than Verilog. But yeah, I'm not quite sure how to answer that question. I feel like people who are comfortable using Scala and Chisel are especially likely to be able to make the jump to using these tools, but maybe not your random hardware engineer.
All right, let's thank Adam. All right, so that concludes our workshop. Hopefully everybody enjoyed learning a lot more about open agile hardware design and have opportunity to hear from people from architecture, from circuits, from algorithms, from EDA, and even from PL. And hopefully this will spark more discussion.